molecular dynamics from the hard sphere problem to biomolecules. So this title is very general, and I suppose that young people who want to know more about this field, the field of computation, about the field of molecular dynamics, will be interested in this lecture, and they can join us in our research. So probably not so many young people in this room, but we also have some people joining in Zoom, and I really hope that the number of our participants this time increases. Now it is early morning, especially in Spain, in Italy, so people maybe will join later. So in my lecture, I would like to give some historical preface about this method, about the development of the method of molecular dynamics, some basics of this method, and then I would like to give some examples where molecular dynamics simulations are used for the study of different systems, and I will be focused on DNA, and I will tell more about the structure of DNA and some particular results. And in the end, the conclusions describing all the lecture. So if we go to the history, this method, the method of molecular dynamics, is based on equations of motion, and of course we have to understand that this is the equations from classical mechanics, Newtonian equations, which can be solved exactly for two-body problem. And it is a unique problem that may be solved. So two-body problems is one of the problems that can be solved analytically. And even if we have three bodies, this problem cannot be solved, cannot have analytical solutions. And if we have even small changes of the initial conditions, as a result, we have unpredictable behavior of the system. So this system, even in the case of three particle, we can't solve analytically. And this it was challenge for many mathematicians, many physicists who studied this problem, and with time it was shown by a mathematician from Finland that it is possible to solve this problem and to obtain the result in the series of infinite series with negative and fractional exponents. This is the mathematician Karl Sundman, and it is possible to obtain the solution in such infinite series, but it's impossible to use this solution in practical way. So, in fact, this problem is unsolvable, and it's very difficult to have to obtain some analytical solution. We are working with the system of many particles. It is important to characterize somehow the system, and we can mention that more than 120 years ago, thermodynamics and statistical physics was born, and you can see these famous people who were in the basis of this science. But if we want to solve the equations of motions for many particles, it is practically not solvable problem because we need to write many differential equations, and it is impossible to solve them analytically. And it was more than 120 years ago, but if we go to the computer era, we can expect that we can solve something with our computers. And here I just show this picture to highlight that computers were different in different time. And here you can see these huge computers which were developed in middle of the past century. One of this computer was developed not far from this place near in California by Lebedev. And it has such a big shape, and this computer was the first in Europe. In the same time, in 1952, it was developed, it was constructed another one computer in Los Alamos laboratory by Nicholas Metropolis at his group. This computer has the name MANIAC, mathematical analyzer, numerical integrator, and automatic computer model. You can see that it is also huge. And on this computer in Los Alamos, it was solved the first, probably the first physical problem, which we know. So this is the problem that has the name Fermi-Pascal-Ullam chain. And in Los Alamos, Fermi stated such problem for mathematicians Stanislav Ulam and John Pasta and a young PhD student Mary Zimbo to solve the problem of connected particles with nonlinear springs and to analyze the thermalization of this system. And they found that this system has very complicated behavior, and with time the modes have different power. So this problem that started to analyze in computer generated new field of research, and Fermi-Pascal-Ullam single chain now is still studied as a fundamental problem. And what is the main idea of the method? So if we have a lot of particles, we need some positions at the initial time step, and also we need velocities. At the initial time step, we have acceleration equal to 0, and then we can calculate the position in the following time step according to formula from mechanics. And the acceleration can be calculated from the second Newtonian law from the force, which is calculated as minus gradient potential energy. You can see here we have the potential energy, which is very important because it describes the system. It describes how the particles interact between each other. And after that, we can calculate the following time step with the using the accelerations that we obtain from the force, from the potential, and also we can calculate the velocity. And then we move to the we do the next iteration, and in such a way we calculate the trajectory of each particle, and we can have the evolution of the system. To integrate the equation of motions, usually is used. Usually the Verlet-Stormer algorithm is used. This algorithm is based on such idea that we can expand the position of the system, the position of the particle in the Taylor series. We have the initial position, after that zero order approximation, after that the first, the second, this is the velocity, this is acceleration. And the same we can do for the previous position, so for the position at the time moment t minus delta t. And we have the same expansion, but with another sign. Here is minus, here is minus. And when we sum two equations, we have such equation which connect the next position of the particle with the previous time step and the time step in t minus 1 in the step. And it is important that this method has it is precise as delta t in power 4. This algorithm was developed by Verlet and Stormer, and according to the history that now is known, the first it was the same algorithm was used by Delambre for the calculation of trajectories of planets. It was much before Verlet and Stormer. And this idea and these algorithms are used to calculate the different systems. And the first system which was calculated, it was the system of hard spheres. It was done by Alder and Wainwright for 32 hard spheres, very small system. And they did this in that time supercomputers in 1957, and later in 1974 it was solved the problem for the hard spheres with Lennard-Jones potential. This potential includes the repulsion, and also it has some attraction part. And this is like a model of liquid ARPA. So you can see this radial distribution function, which is the result of this calculation, and this is the result which can be compared with experiment, which is very important because in this case we have the result which a concrete result from molecular dynamics. Another one important feature of molecular dynamics, which should be mentioned, is that the use of periodic boundary conditions. This is the method how to model the infinite system. Of course, we cannot take many particles. So if we need to calculate the system for a thermodynamic system, we need to take number of particles which equals to about n Avogadro. But of course, it is impossible even now. And we use such method when we take some simulation box. And if some particle goes out from the simulation box, another one particle can goes into the simulation box with the same velocity. And in such way, we model the system as infinite. This method is used now everywhere in any simulation. And it was introduced by Nicolas Metropolis and his colleagues Marshall Rosenblatt and his wife Anna Rosenblatt. And this is the simple systems. This is like hard spheres and like carbon. But what we have in the case of molecules, especially in the case of biomolecules like DNA, like proteins, I just remind that DNA has the shape of the double helix with nucleotide pairs inside. These nucleotides are paired by hydrogen bonds and have some rule according to which they are paired. This is complementary nucleotides. Adenine is always paired with thymine when with cytosine. And in the case of proteins, we have polyamine chain, which also shapes in helix. It is right-handed. It is right-handed and it is stabilized with also with hydrogen. To obtain these models, to discover these molecules, people used a simple way to model the molecules. They just used some walls to connect them as atoms, and also some pieces of iron maiden details to connect different atomic ropes as puzzles in the shape of the molecule. So this is the first way how to model the molecules. And of course, now we use the computers, but in that time, it was only one way to model such big systems. And what is very important is that we need also to take into account the environment. In the case of DNA, environment is extremely important because it stabilizes the structure of the double helix. DNA has hydration shell, which is an integral part of DNA, and it stabilizes the system. And also the ions, which are also necessary to neutralize the phosphate groups. DNA has negatively charged phosphate groups, and if we don't have if we have this don't have the ions, so this system will be unstable. And I like very much this comparison of the DNA double helix with it is considered as electrostatic bomb. It is considered as electrostatic bomb, and I saw this in this paper by Aximentiev, Professor Kornish, colleagues, who did this comparison. So usually we use as counter ions sodium, potassium, other ions, also molecular ions, putrescine, spermidine, spermidine, this time anyway. So I just would like to say that these counter ions, we have some fundamental problems which are related to the distribution of ions, and we have several models which can describe this. And one of the simplest models describes DNA, and actually any polyelectrolyte molecule has a chain of charged particles, and these particles we need to understand how these ions are organized around this system. And it was developed such model where the electrostatic repulsion between these particles is described using the potential with device screening, and in this case it is possible to obtain analytical expression for energy, and also some part describing mixing of ions which are close to the system and which are in the solution. And then if we, okay, thank you. And then according to these conditions, the minimum of energy, we can find some result which allow us to estimate the number of ions which neutralize each phosphate group. So this result is, for instance, for bDNA, the B conformation of the double helix is 0.65. So it means that for 100 phosphate groups, we have 64 ions which neutralize the. So this result, this model is very simple, but it helps us to understand the physics, how these ions are organized around DNA, and in more details you can find in the presentations that we can listen on Saturday, the presentation by our colleague Bogdan. And also, of course, we have other models. I don't stop in details on this model. This is a model where DNA is presented not as a chain of charged bits. This is like a charged cylinder. And we can use Poisson-Boltzmann equation for this and to have some solutions, analytical solutions in the Debye-Hückel approximation, in Kachalsky approximation. And these solutions are studied. And time to time we have papers about this problem, and some new solutions can be found for some particular cases. And also it's very interesting that in general, this equation, Poisson-Boltzmann equation for such system can be reduced to Penrose-Lee equation if we use such variables. And just a few words about analytical models, not simulations, is that we also can use another approach to consider this system, the system of DNA designs. We can consider the system as a lattice, as a system with explicit ions which neutralize the phosphate groups. And we analyzed the system for vibrations, and we found the vibrations of counter-ions with respect to the phosphate groups, and these vibrations also were detected in experimental spectra, in Raman spectra, in the low frequency range. So this is, of course, we can extend this story about models, and here I would like to show a slide with people who contributed a lot to the development of the models, modeling of biomolecules in Ukraine. I would like to mention Professor Alexander Davidov, who was a famous theoretician, physicist, director of our institute. He worked in many fields of theoretical physics, and in particular, he was interested in biophysics, and he introduced his idea of solitons. It is known as Davidov solitons. And this idea had a great impact for the development of many problems in biophysics. Also, Viktor Danilov, who studied electronic structure of DNA, Dmitrov Varun from Institute of Molecular Biology, studied also electronic structure of nucleotides. Professor Sergiy Volkov, who developed a Formas model. Vladimir Maleviev, Anna Shestopalova. This is the Kharkiv School of Biophysics, and also many biophysicists in Ukraine, also in Kharkiv. There is a strong group established by Professor Blagoy and many other people. I don't show all the people here in the slide. So I would like just to mention that we had a strong background in this field. And if we are returning back to the computations of biomolecules, From that period when people model a system with different pieces of describing biomolecules. And now, of course, we use computers. This is a computational cluster, and we have a computational cluster in our institute, which one of the most powerful in Ukraine, and it works all the time in the present days without interruption of our calculations. And of course, we have a lot of software. Some of them is free of charge, some of them is commercial, but nevertheless, we have this software which allows us to make the analysis. And here I show just some program which I like and I use. So this is VMD. It is free of charge, and everybody can download it and can use it. We can do the simulations on at different levels, at the electronic level, and we use quantum chemical calculations like DFT. This is the size of the system of 10 angstroms and the time scale of 10 femtoseconds. Then we go to the atomistic level, and here we use classical molecular dynamics, and here the trajectory is much longer, about 1 microsecond and about 100 angstroms size of the system. There are some hybrid methods between electronic and classical molecular dynamics. This is QMMM, quantum mechanics, molecular mechanics, and we will have a lecture tomorrow in the morning about this method. Also, we have coarse-grained models where the trajectory is up to 1 millisecond, and the system is thousands of angstroms. And also there is a hybrid method between classical molecular dynamics and coarse-grained molecular dynamics. And this field of research, this models will be described in a lecture by Professor Francesca Mocci. It will be on Saturday. Also in different levels, we have different methodology. And of course, in the case of electronic level, we have we solve Schrödinger equation for the system, for the molecule with electrons. At the atomistic level, as I described above, we solve equations of motion, and as well as in the case of coarse-grained models, we also solve the equation of motions, but for the system describing the atomic groups as some masses, units interacting with each other, and as a result, we can have different models of the same molecule. And in this case, we need to find potentials. So, highlighting this methodology, we can say that the electronic level is like a real system, and if we go to the atomistic level, this is like the point graphics of this picture. It is still recognizable, and we can recognize this word. And the coarse-grained model is the figure composition, which describes this system, but it is very rough. We can still recognize it, but it is much different. There is much difference between model and real. To realize all these methods, there are a lot of different software packages where molecular dynamics is implemented. Here I show some paper, which was one of the first describing the simulation of DNA with ions. This is a real system. I mean, there are some water molecules around, there are some ions, And this system is not so large, only 5 nucleotide pairs, but we have 830 water molecules, very short trajectory, but we have also ions, and this is the system which is very, very close to reality. And it was done in middle 80s by Coleman Grove, and Peter Coleman was in his group. It was developed amber force field. It is very popular for the molecular dynamics simulations. And also we have other software packages. This is, for instance, NumT developed in Klaus-Schulte Grove, Gromax developed in Branson Grove. Also, it is important to note that there are a lot of methodology implemented in these work packages, in particular, very important particle mesh evolve method implemented by Pedersen. And great contribution was done by Marshall Levitt, Warshall, and Karpus. They received Nobel Prize in 2013 for this, and Martin Karpus in particular was the developer of charm force field, and also Professor Adolfsson, who was the first who used evolve method to describe electrostatic interactions in the system with DNA. And he also started the software M-Dynamics. This is well-known software for molecular dynamics. So to calculate these trajectories within the framework of all the software packages, we need to know the interaction potentials, and in each of these software packages, the following interaction potentials are used approximately without changes. So this is the potential describing valence bond as interaction between two atoms in a chemical bond. Valence angle, this is the potential describing the angle, valence angle between atoms. Dihedral angle describing change of dihedral angle of 4 atoms. Also some special potential improper tension. It is it describes how one atom can go up from the plane of atoms, and also Urey-Bradley describing it may be used or not, describing the interaction between non-bonded atoms, and long range electrostatic interaction and van der Waals interaction, which is usually modeled with Lennard-Jones potential. So this is the potentials which are everywhere in all these software packages. So the difference, the most important difference is in parameters which are used here. You can see here, this is the parameters, this is the force constant, this is the equilibrium positions for each atom, for each chemical bond, for each angle. And the set of these parameters we call force field. And here you can see the snapshot from file where all these parameters are listed. And you can see here the molecule. This is the nucleotide. And you can see the names of the atoms that they have according to the chemical, according to the chemistry of this system. And in the force field file, to each atom we have another one name which is used in the file of the phosphate. So after this definition, we can go to the potentials. And for instance, here, this is the potential. This is the parameter describing dihedral potential. For instance, here you can see the names of the atoms according to the force field file. And we can find that HN1, this is nitrogen N6, CN1, this is C6, HN1, this is N6, and HN1, this is this one atom. So we, in such way, determine that these three atoms have the potential dihedral angle with such parameters, the force constant and the equilibrium constant. So, and in such way, we have the definition for all interacting atoms, and we determine this system. This is very important part because force field is very important in simulations, and the developers of the force fields spend a lot of time to develop the most appropriate set of parameters. For instance, in the case of the charm force field, there are more than 30 versions of these force fields which are upgraded, and with time these force fields are become better. So if we are going to the concrete results, concrete examples that we have according to the concrete examples that we have from this method, I would like to show several results for DNA designs. This is DNA with metal ions interacting with atoms. And here it was studied the system. It was studied the influence of hydration of these ions, because metal ions have different hydration, and we found that this is an important feature that we should take into consideration to analyze the distribution of the ions around DNA. Also, it is very important that if we have molecular ions, they bind to DNA in another way, because they can change the shape and they go inside the different regions of the DNA double helix, in particular to the minor groove of the DNA double helix, and we found that it happens in the narrowest place of the double helix. And due to the sequence dependence of the width of the minor groove, there is a sequence specificity of polyamine localization on DNA. And also what we found is that polyamides are very flexible, and this feature is very important for interaction with DNA. So polyamides can bend and form different conformations. We analyzed all these conformations, and we found that in the case of this particular polyamides pyrimidine, we have 7 families of conformations. This work with polyamides was done in collaboration with Francesca Moccia, Apalaxonen, and our colleagues, and this work continues. Also it's interesting if we look at the system of these ions in electric field. In this case, the ions move along DNA, if this field is parallel to the double helix. But if this field is orthogonal, the DNA double helix can be destroyed. In some paper, we found that this process, the process of DNA melting, depends on frequency of electric field. So the simulation was done for the system with alternated electric field, and this is very interesting because in this way we can influence also melting of the double helix. So this is we took these two papers are in the same time, 2020. And another one interesting result, which I wanted to show you, was obtained by Aximentia group in Urbana-Champaign, the University of Urbana-Champaign. This is an example how the DNA can rotate as a response on motion of ions in the external electric field. And this rotation appears due to the special structure of the double helix, due to the grooves ions move along DNA, and these ions this motion induce the water flow, and due to these grooves, DNA starts to rotate. And this is like a tiny electromotor, and we had this spring, we had a meeting organized in our institute, supported by American Physical Society, where Professor Aximentia described in details this very interesting result. It is very important that the simulations can be used for different purposes. First of all, of course, it is important for biophysics. It is important to understand the mechanisms of biological functioning of DNA and all in general biomolecules. But now it is a very interesting and rapidly developing field of research related to biomaterials. And in this case, DNA is very promising biomaterial because this molecule has unique properties, providing very important features that can be used in technology. In particular, this is, I already mentioned, this is the property of nucleotide pairing, which allows to build some smart materials like DNA origami, and these materials can be used to construct some simple shapes. Here you can see even boxes made of DNA, and they are constructed on the basis of this concept. Another one important feature of DNA is that it is highly charged. So as I mentioned before, this is like electrostatic bomb, and each phosphate is negatively charged, and the counter ions bind to DNA, and the system has very interesting features. The last one important feature that I would like to mention is that DNA is everywhere, and this is abundant material that we can find and we can use. So the amount of DNA is comparable to the amount of oil in the world, and this is a huge amount, which can be which allows us to use DNA in practical sense. This is already done, and I would like to show the results, to show some already working technology. This is lithium DNA supercapacitor developed in South Korea, where DNA gel is used as electrolyte between electrodes in battery. And this gel looks like this. So you can see this. This is just a simple gel, and it is very important to understand the structure of the system, the structure of DNA with lithium, and in this case, it is important to do additional experiments, and we collaborate with our colleagues from Taras Shevchenko University, from physics department, and we analyzed the conductivity of the system of DNA with lithium, and we found that DNA constrains lithium ions essentially. But to explain this, we need some additional analysis. So we have some assumptions, but we need to conduct some simulations, and we have done the simulations. It was done just recently. Tatiana Buban will tell us about these results tomorrow morning. So this is DNA molecules in the solution with lithium chloride of different concentration, and we will have a special lecture tomorrow about this. So also we can have other applications, and I just need to speed up. So there are a lot of applications which are based on properties of DNA in the case if DNA is conductor. And also there are some already developed technologies to record the information on the genome with the use of DNA molecules. And also there are some assumptions about DNA as a perfect quantum. So but this is on the assumptions, so I don't know how it can be. Probably we will have answer for this question soon. And today we will have a lecture about quantum computers by Christine Magnetic. And if we are talking about DNA as conductor, as for me, I suppose it is very important to understand such system like DNA with metal ions in sense of metallization of DNA when the ions are inserted inside the DNA macromolecule. And here you can see experimental results. This is the X-ray structure of the DNA double helix with silver ions, argentum inside. This is X-ray structure, and also there are other experimental work with NMR structure, where the ions also inside, but these ions have different organizations. So here you can see this line of ions, line of argentum is straight, and in this case it is goes according to the helical structure of DNA, and this is because in the case of the first structure, here we have some nucleotides which are pushed up from this double helix. And also what is interesting is that also argentum clusters can bind to DNA. And there are some experimental results and quantum chemical calculations, quantum mechanics, molecular mechanics calculations, showing how this argentum cluster can be intercalated between nucleotide pairs. So this is also very promising field of research. And always, in the case of these papers, in the case of these systems, it is always expected that this system will have some special characteristics for conductivity. And that's why it is very interesting to analyze if we have here the conductivity or not, or what will happen if we decrease the temperature, for instance, for this system, and so on. So we started to study the system. This is some preliminary results which we just received for DNA nucleotides and argentum ions, and these results will be described in details by our colleague Yevgen Osokin. It will be on the side. So in the end, I would like to finish with such scheme. describing different applications that can be studied experimentally, theoretically, with different methods, calculation methods. In the case of DNA, with metal ions. And here I just highlighted some results related to metallized DNA, lithium-ion battery. We will listen to those results in details later. DNA in electric field. And also there are many other applications that we can consider, and we can use atomistic molecular dynamics and also quantum chemical calculations and other methods for the study of this system. This is a review which we recently published in Small Structures with our colleagues from our institute, Marcin Shibotario, and Attila Tsonen and Professor Francesca Nucci. So in the end, I would like to thank my colleagues from the institute, from our department, Professor Volkov, Professor Yevgen Deshkot, Dmitro Vyakovsky, Tatiana Gluban, Alexei Zarevsky, Yevgen Osopin, Bogdan Rishov, and Polina Kanevska, Vitaly Demchishin. Our collaboration with colleagues in the field of computations with Professor Francesca Nucci, Attila Tsonen, Tudor Vasilyev, and all our colleagues, and also our experimental collaboration with colleagues from Taras Shevchenko University, Professor Bularin, Maxim Lazarenko, Alexander Alexeyev, and students. So, and I would like to thank Foundation, National Research Funds, Foundation of Ukraine, for funding our research. So, and thank you for your attention. So, if there are questions, please, I'm ready to answer. Yes, please.
Thank you very much. Absolutely great lectures. And especially for me as a biophysicist, the implications of all these researchers are very important and interesting. What about the works which you described as for DNA models and the lithium batteries? Are they on the stage of modeling, or do you have the examples of realization experiments or already technological realization, because it's interesting direction? Thank you.
Thank you very much, Professor Vlada Pashinska. We are very glad from Kharkiv. Yes, we are very glad that you came. And in the case of lithium-ion batteries, this is already developed technology. It is already used. And there are several patents from South Korea. They started companies, private companies, startups, and they do this. So actually, they move in the direction to change lithium for sodium. It's clear why, and they have success. But of course, there are fundamental problems which I showed in these slides about structure of lithium gel, because this scheme which they propose, this is from the paper, it is not really like this. And it is important to understand, because they have some dependence on structure, dependence of conductivity and other properties of this gel on this structure. So it is important to understand how it is organized. And it works. So I didn't show the video where you can find some electrical mechanisms, something is working, and so on. So, and this is about lithium-ion batteries, and it is already working, and this field of research is is very close to the direct implementation to technology. And what is about electromotor? This is on the level of simulations. And the reason is because we need to apply very high electric field. So in the simulation, we have very high electric field. We have to start moving exercise was the first. But this is not because it's impossible. This is because of our simulation. I suppose probably it is possible, but maybe it is technically very difficult to implement the test. I have not seen yet electromotors like this. But there is another one electromotor, which is based on the conformational transition from right-handed to left-handed DNA. This is slightly different, but it is realized experimentally. And in this case, DNA also rotates, and some rotation can be used for to create an electron.
Thank you.
Thank you. Yes, yes, please.
You speak about device shielding in early stage of, and this means that potential energy is much smaller. But later it was supported by modeling molecular dynamic.
Yes, this is a very good question because in fact this idea with the use of device screening and further approximations which are used in particular, maybe it is more convenient to go here. For instance, the biphasic approximation, which we know that this condition should work. Actually, it doesn't work in the case of DNA. But if we do this approximation, we obtain some results which agree well with experiment, and it makes some question arises why. So there are some analysis of this problem, and some more realistic models are developed, like here, like the Chayefsky approximation, where only the ions of opposite sign are taken into consideration, and as a result, some analytical solution is obtained. So it is possible to have some solution without approximation of this smallness. Yes, it is possible, but this is challenging. And in this papers, you can see this is with letters. So this each one solution. This is something new in this field. So this is really extremely difficult. Thank you.